Hello, I'm Nitisha Jain, a PhD student at the Hasso-Plattner Institute in Germany. I'm talking about a research paper improving knowledge graph embeddings with ontological reasoning. This work was done in collaboration with researchers from the Bosch Center for Artificial Intelligence in Germany. Knowledge graph embeddings are aimed at embedding the components of the knowledge graph, that is, entities and relations, into continuous vector spaces. This way, we can have easy manipulation of knowledge graph data, while at the same time preserving the inherent structure of the knowledge graph. This enables us to capture the interactions between the different entities of the knowledge graph. So for example, on the right-hand side, we have a translation-based KG embedding, where we can see that the vectors for these entities are close together in the continuous vector space. In the recent decade, knowledge graph embeddings have gained considerable popularity. Many different embedding models have been proposed, such as Trans-E, ReSCAL, and so on. And many different models are also being proposed every year. These embeddings have found many applications. The main application being a link prediction for knowledge graphs, aiming towards knowledge graph completion. Other applications are entity similarity, relation similarity, and entity clustering, and so on. We have seen in our experiments that despite showing good performance for the link prediction task, embeddings can sometimes have semantically incorrect predictions. For example, for a triple Mike works at, the predicted entity should be of type company. However, the predicted entity could be John, which is of type person. This is clearly semantically incorrect. This can happen because knowledge graph embeddings have been trained on existing KG facts only, without any knowledge of the ontology that is associated with the datasets. Therefore, it is important that the training process be made semantically aware to avoid any nonsensical or undesirable predictions. Let us have a look at how the knowledge graph embeddings are trained. During the training process, negative samples for each positive sample are being generated automatically. This is being used for scoring. The idea is that the model is trained to rank the positive triples higher than the negative ones. Here we see a typical training process where a knowledge graph triple such as Mike works at Bosch is given to the embedding training along with a set of negative samples generated automatically. Once these samples are provided to the training process, the idea is that the model learns to have higher ranking for the correct triple, that is Mike works at Bosch, and a lower ranking for the incorrect triples. So when the predicted triples are seen, the correct ones rank higher than the incorrect ones. The task of negative sample generation is a challenging one due to the open world assumption made by knowledge graphs. Currently, techniques such as random generation of negative samples or local closed world assumption based techniques are being used. However, there are many shortcomings to these approaches. They might lead to false positives, that is, they might generate negative samples that are actually true in reality. Also, these might lead to semantically inconsistent predictions by the resulting embedding models. This is due to the fact that ontology is not taken into consideration while training. Recently, a technique was suggested this year, which is ontology-aware negative sampling. Here, a subset of negative samples is pre-computed, and this is based on disjoint entity types. However, this approach is a static one. Therefore, the similar sampling for all triples in the knowledge graph is done, and this way, the difficult cases or hard to predict cases are not really targeted. We have proposed an ontology-driven and dynamic negative sampling technique in this work, and we call it the Reason KGE. To further discuss our approach, let us consider this example knowledge graph and the accompanying ontology. The ontological axioms state that the domain for the works at relation should be person, the range of the located in relation should be location, and the person and the location classes are disjoint with each other. Let us consider that an embedding model was trained on top of this knowledge graph, and we have a bad prediction, Bosch located in John, which is semantically incorrect. The goal of our work is to increase the prediction accuracy of the embedding models. The idea is that we will detect the inconsistent predictions made by an existing embedding model. And once we have the identified inconsistent predictions, we use those triples as feedback, as negative samples for the next iteration of training. Therefore, we perform ontological reasoning for detecting the inconsistent prediction, and then we have a negative sampling technique using those triples as negative samples for the next iteration of training. So here we have a standard embedding method where a default negative sampling technique is used to train the model in the first iteration. Then we have a reasoning-based method, reason KGE, which, starting from this base embedding model, will perform consistency checking with the help of the ontology, detect the inconsistent predicted triples, and then generalize them to create a set of negative samples. This set of negative samples can be used for a further iteration of training of the embedding model. This way, multiple iterations can be performed. Within each iteration, the negative samples will be dynamically generated. Let us consider one of the novel features of this approach, which is the consistency checking module. In the consistency checking module, we want to find out whether the predicted triple from the model is consistent with the existing facts in the knowledge graph and the ontology. However, for large knowledge graphs, this reasoning process can be quite slow, and therefore we want to avoid checking the whole knowledge graph for each individual prediction. For this, we leverage existing work and create a relevant set of triples for each predicted triple. For each prediction, we will find all the triples from the knowledge graph where either the subject or the object entity is present, and this way obtain a subset of the KG. We assert that if the predicted triple is consistent with respect to the relevant set and the underlying ontology, then the predicted triple would be consistent with respect to the whole knowledge graph and the underlying ontology. To illustrate this, let's have a look at our example knowledge graph and the prediction Bosch located in John. To find the relevant set for this predicted triple, we will look at all the triples in the knowledge graph where either Bosch or John is present as one of the entities. So for John, we have the triples John type person, John friend of Bob, and John lives in Germany. Whereas for Bosch, we have the triple Bosch type company. All these triples constitute our relevant set for this predicted triple. This predicted triple, the relevant set, and the ontology are all given to the reasoner for performing the consistency check. We can see here that the predicted triple is inconsistent because the type for the entity John is person, but the range for located in relation should be location, and person and location are disjoint classes. Therefore, in this case, the reasoner can predict with the help of the relevant set only that this particular prediction is inconsistent. And this way we can perform fast reasoning. Let us now talk about the generalization module. The idea of generalization is that we need not only one, but several negative samples for each training triple in the knowledge graph. Therefore, the idea is to generalize the inconsistent prediction and obtain a set of similarly inconsistent fact from within the KG. The approach here is that we want to detect the inconsistency pattern from the wrong prediction and then generate similar other patterns from the knowledge graph triples. Looking at our example, we see that John is the incorrectly predicted entity. And this is because John is of type person, which is ontologically inconsistent. We can look at our knowledge graph and look for other entities which have the same property. For example, we have the entity Bob here, which also has type person and has similar connections as John. So it is estimated that this entity will also cause similar inconsistency. Therefore, we can also have Bosch located in Bob as another negative sample, which will cause the same kind of inconsistency. Such triples can constitute the list of generalized samples that can be given for the next iteration of embedding training. The purpose of generalization is twofold. First of all, we are able to obtain this way sufficient number of negative samples for retraining the embedding model. Also, this way, the embedding model learns the wrong patterns during the training phase, and thus it is able to avoid these same wrong predictions in future. Let us now have a look at the experiments that we performed to demonstrate the performance of the reason KGE method. We have taken real-world knowledge graph datasets such as Yago 310 and DBpedia 15K for our experiments. We have also taken a synthesized knowledge graph Lubum 3 for our experiments. Trans-E and complex were the embedding models that were used in the experiments. For our baselines, we considered the default sampling, where random generation of fixed number of negative samples per triple is performed. We also took the static sampling approach, which was earlier proposed this year, which is also taking into account ontology, but does it in a static manner. For all experiments, we kept the number of iterations of our sampling method to 2. For the link prediction performance, we show here a subset of the results in terms of the hits at 10 metric. We can see that for both the embedding models as well as the knowledge graph datasets, Yago 310 and DBpedia, Reason KGE is able to outperform the default sampling as well as the static sampling technique. We see that the performance is especially better for the DBpedia dataset here. In addition to the link prediction performance, we also measured the ratio of inconsistent predictions. This is done by looking at the top 10 predictions from the embedding model and measuring how many of these are inconsistent with respect to the underlying ontology. We can see here that in most of the cases, Reason KGE leads to fewer inconsistent predictions, which demonstrates the benefits of using this method. It is also to be noted that Reason KGE can be employed on top of any underlying embedding method and thus lead to its improvements. In summary, in this work, we have discussed that knowledge graph embeddings can lead to inconsistent predictions with respect to the ontologies. Therefore, ontology-aware negative sampling methods are needed for training the embedding models. To this effect, we have proposed a novel approach called Reason KGE, which is ontology-driven and operates in an iterative fashion. This leads to dynamic generation of negative samples and feedback to the next iteration of the embedding method. Overall, this leads to better link prediction performance and more consistent predictions by the resulting embedding model. We would be happy to discuss further on this, and any questions and comments are most welcome. Thank you.